Hi, everybody. Welcome to our Music and Math Expo. We are the Washington Student Math Association.
So we're going to break our presentation up into 4 parts. The first one is going to be an introduction to all of the music theory that you're going to need to know for the rest of the presentation. The second one is going to be using these concepts to connect music to their physical manifestation of sound waves. The third part is going to be using what we've learned about music and sound waves to determine what makes two musical notes sound good or bad together. And then the final section will be using all of that to kind of explore some really fun applications.
So we will start off today's video with introduction to music theory. Our musical notes are measured numerically based on their wavelengths. We measure frequency by the number of full cycles a wave goes through in 1 second. 1 hertz is equivalent to 1 cycle per second. For example, if we want to know the frequency of the note A4, we can see that it goes through 440 wave cycles in 1 second, showing that it is 440 hertz.
Next, we're gonna talk about harmonies. Harmonies are two more notes played at the same time. Chords, they are the most basic unit of harmony, consists of 3 or more simultaneous pitches. And if we look at the intervals to the right, we have unison, major minor second, major minor third, perfect fourth, tritone, which has augmented fourth or diminished fifth, a perfect fifth, a major minor sixth, a major minor seventh, and another perfect note which forms the octave. Triads, they're chords and they have 3 notes which has the note the root, which is a unison. The third can be either major or minor, and a perfect fifth.
So let's discuss the parts of a wave. There's the amplitude, which is the distance between the equilibrium and the compression. And then this is also equal to the distance between the equilibrium and the rarefaction. Then there's the crest. The crest is the maximum point at which the wave reaches. And then the trough is the minimum point of which the wave reaches. And then the wavelength is the distance between trough to trough or crest to crest.
Now that we know the parts of the wave, we can talk about how they affect the sound. Amplitude is a measure of loudness and the distance between the equilibrium and compression, as Nisha mentioned. Depending on the size of the amplitude, the sound is either louder or quieter. Similarly, frequency is a measure of the number of waves that pass through a given point in a certain amount of time, which is called the period. And the more waves that pass through, the higher the pitch, and the lower the pitch. Fun fact, we have a different range of frequencies that we can hear, and frequency is measured in hertz.
So next we're going to learn about some of the mathematical relationships between music and math. And the first relationship is between the period of a wave and frequency. It's shown by the 2 equations on the slide. The equation is the period equals 1 over the frequency, which means that they're inversely related. Additionally, we have another equation, which is velocity equals frequency times wavelength. So if you have 2 of the characteristics of the wave, such as like the frequency and the velocity, you can find the wavelength, or the frequency and the wavelength, you can find the velocity.
So now we're going to talk about how these concepts influence what kinds of notes sound good together and what kinds of notes sound bad together. So when 2 musical notes are played together, they create sound waves, and these sound waves can line up and match in different ways. And so sometimes 2 notes will have the peak and the dip of their sound wave at the same time, and this creates notes that sound pleasant together. But other sound waves can peak and dip at differing or just completely opposite times, and this creates notes that sound worse or dissonant together. And the way this is determined is with the ratio between the frequencies of the waves. And so if the ratio between the hertz values of 2 sound waves is has a small denominator, for example 1/2, then they'll peak and dip at the same time more frequently and the note will sound better. Whereas if it has a large denominator like 15/16, then they'll peak and dip at differing times more often and they'll sound worse together.
So we have some examples of these, and the first one is an octave. So these two notes are a ratio of 1 to 2, and the two notes are A3, which is 220 hertz, and A4, which is 440 hertz. So these two notes sound together because they contain two notes of the same name and have the simplest ratio of any notes. So therefore, they should sound the nicest together. On the next example, we have our thirds. These two notes have a ratio of 5 to 4, and the notes are D4 to F sharp 4. So one thing to note is that the ratio of frequencies does not equal the musical interval. For example, a third does not have a ratio of 1 to 3. And this sounds worse than octaves because the ratio is larger.
All right, now let's look at the minor second. So in the example that we gave out just now, the minor second notes was C4 to C sharp 4. And now you might have noticed that these two notes did not sound very well together. Well, this is because the ratio of these two notes is 16 to 15. And because the ratio of these two notes is so big compared to the ratio of notes like octaves or thirds, these notes clash more together than other chords. Now, looking at the graph to the right, we see that the waves over time, the peaks and valleys of the waves become more and more offset, as you can see in the graph. And because of this, we can see that this makes the notes sound more and more clashy together instead of syncing with each other. Now, keep in mind that not all notes are perfect pitch. Some notes may be slightly sharper or flatter, which would also distort the ratios of the notes significantly. Okay, now we can talk about constructive and destructive interference. When two notes are played together and the waves are added together, one of two scenarios can occur. The first of which is constructive interference. This happens when the peaks and troughs of the waves match perfectly and the resultant wave has an amplitude which is the sum of the amplitudes of both waves. Now we can look at the image to the right, and we can see that when you add two waves that have the same peaks and dips, we end up with a wave that has peaks and dips with twice the amplitude, which makes the sound twice as loud and twice as good. And secondly, we have destructive interference. Destructive interference happens when the peaks and troughs of the waves perfectly alternate with each other, and the resultant wave is non-existent because each wave cancels out with the other one. And now we can see this through the bottom image on the right, in which we have two waves where the peaks and troughs are exactly opposite of each other, which results in a singular line, which shows that the wave itself has been canceled out.
All right, now for some applications. So noise canceling headphones don't actually block any sound. They use little microphones to pick up tiny background noises and emit the same sound with an exact opposite wave using the destructive interference, and it reduces the sound to silence.
What is Blob Opera? It is another example of applications of sound waves. Blob Opera is a collaborative project created by David Lee in partnership with Google Arts and Culture. Blob Opera is an AI program that features 4 colorful blobs that you can drag up and down to change their pitch or forwards and backwards to change the vowel sounds.
Now, Blob Opera is connected with this concept called AI, or artificial intelligence, and it's a study of how algorithms improve through experience. A really good example of this is self-driving cars, where the AI system for a car is shown countless images and undergoes different experiences to distinguish the best possible direction, speed, and reaction to their driving situation. Essentially, a car has different sensors just like us, and through receiving data about how other safe drivers react to situations such as a red light, someone passing them on a road, and even the most extreme cases of crash. This receiving of data or input expands upon a car's set of reactions to the ever-growing set of experience. So basically, to create a more advanced system, they feed it data, but they feed it selective data. So what does this have to do with Blob Opera? Blob Opera and self-driving cars are based on the same concept of AI. Instead of car reactions, Blob Opera uses singers. So these singers were some of the best in their craft. And through AI learning of their voices, it was able to create their own version of tenor, bass, mezzo-soprano, and soprano through the blobs. However, if you hear the real singers, you'll see a clear marked difference from the blobs. AI's method of learning is far different from our own. We learn through mimicking and finding our own tones of singing, testing the bounds and capabilities of our voice. However, the AI for the blobs learns mathematically. They can't listen to the tenor the same way we do, but they can see the pitch, amplitude, and frequency of the waves to transform into mathematical equations, such as t equals 1 over f, or velocity equals wavelength times frequency. Each shift in tone creates a new wave, which is a lot of data to imagine and analyze, but these blobs do it to create their opera. So Blob Opera is one of the most advanced programs created in the past decade for AI, since this is a relatively new field. So understanding AI comes from a mathematical understanding of how we perceive waves versus how we can look at waves mathematically. And to get involved with AI, an ability to code and understanding of a unique subject, such as David Lee's opera, is all supported by math. And this ties into our overarching idea for this.
Thank you for watching.